Hello everyone. Myself Mr. S.M. Ganwat working as assistant professor in mechanical department at Sharad Institute of Technology College of Engineering, Yadrao, Ichalkaranji. In this session, we are going to start unit number 1, that is structure of materials part first. In part first, basically we are going to discuss the fundamental concepts associated with structure of materials, and we are going to discuss the face centered cubic crystal structure, and we are going to discuss the body centered cubic crystal structure in this particular session. Now we are going to discuss the fundamental concepts. Before discussing the fundamental concepts, we are going to discuss why to study the structure of crystalline solids. The properties of some materials are directly related to their crystal structures. For example, pure and underformed magnesium and beryllium having one crystal structure are much more brittle, that is, fracture at lower degrees of deformation than pure and undeformed metals such as gold and silver that have yet another crystal structure. Furthermore, significant property differences exist between crystalline and non-crystalline materials having the same composition. For example, non-crystalline ceramic and polymers normally are optically transparent. The same materials in crystalline or semi-crystalline form tend to be opaque or at best translucent. In the processing structure properties performance scheme, reason for studying the structure of crystal solids are as follows. We are going to discuss this with example. A knowledge of crystal structure for iron help us to understand transformation that occur when steels are heat treated to improve their mechanical properties. This is the example to study the structure of crystalline solid. Now we are going to proceed further with the point fundamental concepts. Solid materials may be classified according to the regularity with which atoms or ions are arranged with respect to one another. A crystalline material is one in which the atoms are situated in a repeating or periodic array over the large atomic distances. That is, long range order exists such that upon solidification, the atoms will position themselves in a repetitive three-dimensional pattern in which each atom is bonded to its nearest neighbor atoms. All metals, many ceramic materials, and certain polymers form crystalline structures under normal solidification conditions. For those that do not crystallize, this long range atomic order is absent. These non crystalline or amorphous materials are discussed in next sessions. Now we are going to proceed further. Some of the properties of crystalline solids depends on the crystal structure of the material, the manner in which atoms, ions, or molecules are arranged. There is an extremely large number of different crystal structures, all having long range atomic order. These vary from relatively simple structures for metals to exceedingly complex ones, as displayed by some of the ceramics and polymeric materials. When describing crystalline structure, atoms or ions are thought of as being solid spheres having well-defined diameters. This is termed the atomic hard sphere model, in which spheres representing nearest neighbor atoms touch one another. An example of hard sphere model for the atomic arrangement found in some of the common elemental metals, that is we are going to discuss. In this particular case, all the atoms are identical. Sometimes the term lattice is used in context of crystal structure. In this sense, lattice means a three-dimensional array of points coinciding with atom positions. Now we are going to discuss the unit cells. The atomic order in crystalline solids indicates that small group of atoms form a repetitive pattern. Thus, in describing crystal structure, it is often convenient to subdivide the structure into small repeat entities called unit cells. Unit cells for most crystal structures are parallelepipeds or prisms, having three sets of parallel faces. One is drawn with the aggregate of spheres, which is in this case happens to be a cube. A unit cell is chosen to represent the symmetry of crystal structure, wherein all atom positions in the crystal may be generated by translation of unit cell integral distances along each of its edges. Thus, the unit cell is basic structural unit or building block of the crystal structure and defines the crystal structure by virtue of its geometry and the atom positions within. Convenience usually dictates that corners parallelepiped corners coincide with centers of hard sphere atoms. Furthermore, more than a single unit cell may be chosen for a particular crystal structure. However, we generally use the unit cell having highest level of geometrical symmetry. Now we will proceed further with the next point, that is metallic crystal structures. The atomic bonding in this group of materials is metallic and thus non-directional in nature. Consequently, there are minimal restrictions as to the number and position of nearest neighbor atoms. This leads to relatively large number of nearest neighbors and dense atomic packing for most metallic crystal structures. Also for metals, using the hard sphere model for the crystal structure, each sphere represents an iron core. Three relatively simple crystal structures are found for most of the common metals. First is face-centered cubic, second is body-centered cubic, and third one is hexagonal closed pack. This is the basic fundamental concepts related to structure of crystals. Also, we have discussed in fundamental concept the major points as crystalline structure, its properties. Also, we have discussed what is lattice. Also, we have discussed what is the unit cell. And in further discussion, we are going to discuss face-centered cubic, body-centered cubic, and hexagonal closed pack structures. Now we will start with our first crystal structure, that is face-centered cubic crystal structure. The crystal structure found for many metals has a unit cell of cubic geometry with atoms located at each of the corners and the center of all the cube faces. Once again, I repeat this particular point. The crystal structure found for many metals has a unit cell of cubic geometry. I am going to trace the word cubic geometry with atoms located at each of the corners and the center of all the cube faces. It is called the face-centered cubic crystal structure. Some of the familiar metals having this crystal structure are copper, aluminum, silver, and gold. Figure is going to show you a hard sphere model for the face-centered cubic unit cell, whereas the B figure is going to show you the atom centers are represented by small circles to provide a better perspective of atom positions. The aggregate of the atom in C figure represents a section of crystal consisting of many abscissi unit cells. These spheres or ion cores touch one another across a face diagonal. The cube edge length A and the atomic radius capital R are related through as A is equal to 2R under root 2. For the abscissi crystal structure, each corner atom is shared among 8 unit cells, whereas a face-centered atom belongs to only 2. Therefore, 1/8 of each of the 8 corner atoms and 1/2 of each of the 6 face atoms, or a total of 4 whole atoms, may be assigned to give to a given unit cell. This is shown in figure A, where only sphere portions are represented within the confines of the cube. The cell comprises the volume of the cube, which is generated from the centers of the corner atoms as shown in figure. Corner and face positions are really equivalent. That is, translation of the cube corner from an original corner atom to the center of a face atom will not alter the cell structure. Now, I am going to repeat this particular arrangement. For the abscissi crystal structure, each corner atom is shared among 8 unit cells, whereas a face-centered atom belongs to only 2. Therefore, 1/8 of each of the 8 corner atoms and 1/2 of each of the 6 face atoms, or a total of 4 whole atoms, may be assigned to a given unit cell. This is shown in figure A, where only sphere portions are represented within the confines of the cube. The cell comprises the volume of the cube, which is generated from the centers of the corner atoms as shown in figure. Corner and face positions are really equivalent. That is, translation of the cube corner from an original corner atom to the center of a face atom will not alter the cell structure. Two other important characteristics of a crystal structure are the coordination number and atomic packing factor, that is termed as APF. For metals, each atom has the same number of nearest neighbor or touching atoms, which is the coordination number. For face-centered cubics, the coordination number is 12. This may be confirmed by examination of figure A. The front face atom has 4 corner nearest neighbor atoms surrounding it. 4 face atoms that are in contact from behind, and 4 other equivalent face atoms residing in the next unit cell to the front, which is not shown. Once again, I am going to repeat this particular coordination number. The important characteristics of this particular crystal structure are coordination number and atomic packing factor. We are going to discuss coordination number for this particular concept. For metals, each atom has the same number of nearest neighbor or touching atoms, which is the coordination number. For face-centered cubics, the coordination number is 12. This may be confirmed by examination of figure A. The front face atom has 4 corner nearest neighbor atoms surrounding it, 4 face atoms that are in contact from behind, and 4 other equivalent face atoms residing in the next unit cell to the front, which is not shown. Now we are going to discuss the atomic packing factor, that is termed as APF. The APF is the sum of the sphere volumes of all atoms within an unit cell, as summing the atomic hard-sphere model, divided by the unit cell volume. That is, atomic packing factor is defined as it is the ratio of volume of atoms in unit cell to total cell volume is nothing but atomic packing factor. For the FCC structure, the atomic packing factor is 0.74, which is the maximum packing possible for spheres all having the same diameter. Computation of this APF is also included. Metals typically having relatively large atomic packing factor to maximize the shielding provided by the free electron cloud. Now we are going to discuss the next crystal structure, that is body centered cubic crystal structure. Another common metallic crystal structure also has a cubic unit cell with atoms located at all 8 corners and a single atom at the cube center. This is called as body centered cubic crystal structure. Once again, I will repeat this. This crystal structure also has a cubic unit cell with atoms located at all 8 corners and a single atom at the cube center. This is called as body-centered cubic crystal structure. A collection of spheres of this crystal structure is shown in figure. Figure A, B, C are going to show you the diagrams of BCC unit cell with the atoms represented by hard sphere and reduced sphere models respectively. Center and corner atoms touch one another along cube diagonals and unit cell length small a and atomic radius capital R are related through the equation, that is a, that is unit cell length is equal to 4r divided by under root 3. This is the relation between atomic radius and unit cell length. Now we are going to discuss the common examples of BCC structure, that is chromium, iron, tungsten as well as several other metals are found to be a BCC structure. Two atoms are associated with each BCC unit cell, equivalent of one atom from the 8 corners, each of which is shared among 8 unit cells, and the single center atom which is wholly contained within its cell. In addition, corner and center atom positions are equivalent. The coordination number for the BCC crystal structure is 8. Each center atom has nearest neighbor its 8 corner atoms. Because the coordination number is less for BCC than FCC, so also is the atomic packing factor for BCC is lower, that is 0.68, and for FCC it is 0.74. This is all about the body centered cubic crystal structure. Now we are going to see the reference part. For this session, the reference is William D. Callister Jr., David G. Rethwich, Material Science and Engineering, an Introduction. For further reading, you can refer this particular reference book for Introduction to Material Science and Engineering. Thank you.